Thank you so much. It's such a privilege to be here and listen to all of these wonderful talks and everything that is going on in the world to fight climate change. And here I am to try to tell you a story about how overcoming the limits of computation could also make a contribution. And I want to start with a little personal story. I'm a chemist by training from Germany. And in 2006, we had a very hot summer, World Cup was going on, great, and I was stuck in a lab trying to get an organic chemical reaction to work for my undergrad. Little research project, was supposed to work, didn't work. And I tried to vary everything that I could think of. Temperature, catalyst, solvent, didn't work. And at that moment, I asked myself, why can we not use a computer to simulate what's going on in my flask so I can actually make a decision about what solvent to use, what catalyst to use, and make sure that my reaction works, and then go off and watch football with my mates. And that experience is shared by many chemists around the world doing slightly more important things than that undergrad course, working on drugs, working on better battery materials, working on improving industrial processes that produce chemicals so they become more energy efficient. So why is that so hard to simulate these types of chemical reactions, these types of materials on a classical computer? Fundamentally, it is because we have to look at the electrons, and these electrons are pesky quantum mechanical particles. They behave according to the laws of quantum mechanics and not according to the laws of the classical world. This is the Schrödinger equation, the equation that governs quantum mechanics. And this psi there, this wave function, that's what describes the electrons. And if I wanted to hack that into a classical computer, that's the formula I have to use. I did that for my PhD, by the way, and it wasn't fun. Yeah? It's clunky. It's super clunky. But if we could do that, if we could do those calculations better on a classical computer, or on any computer, really, it would unlock innovation in a vast variety of topics connected to climate change. Because chemicals and materials underpin so much of what we're trying to do in solar energy, in carbon capture, in agriculture. So this is an analysis that colleagues of mine at Intel and a company called Zapata did about where better specific quantum chemical calculations could really help with these aspects of climate change. And if you see a bright orange dot, it will have a big impact. There's lots of bright orange dots here. So having more computational power, a different way of computing, would help accelerate innovation that we need to solve these problems, to improve on these aspects. Okay, now I'm here to talk about quantum computing, right? So enter the quantum computer. The quantum computer is a quantum system itself, right? So it's kind of intuitive that it will be able to represent other quantum systems very well and excel at computing their properties. Quantum computers consist at their heart of qubits, of quantum bits. That's the equivalent of the classical bit. They can be made in different ways, in different physical instantiations, from atoms, from superconductors, semiconductors. You can also use photons. There's many different ways. We're not quite sure what the quantum transistor will be yet. But all of these different ways of making qubits have one thing in common. It doesn't really matter. You can write out this wave function that governs how your electrons behave in your material in a much, much more elegant way. This is a much more elegant formula, without as many sums, without as many indices. Much easier to program. So what's the problem with these qubits? Why don't we have these quantum computers yet? Well, it is because these qubits also have a property that makes it very, very hard to build quantum computers, which is that they all have unavoidable errors. That's due to Heisenberg's uncertainty principle in its heart. They have these quantum fluctuations, and they want to interact with the environment, and as soon as they do, they flatten, they lose their quantum properties, and I cannot do anything with them anymore. So if I say quantum computers consist of qubits, I've made a vast oversimplification. They consist of qubits and a huge life support system around them that keeps them alive and actually performs these computations. And this is how it looks in the case of superconducting qubits today. You have the qubits in this wonderful chandelier. You need a dilution refrigerator because they're superconducting, so you need to keep them very cold. But then you have this whole system around it, consisting of instruments, local computers, a central computer that sends in radio frequency pulses of just the right shape at just the right time to perform the operations and to keep these qubits alive. And with this setup, today I can get to about 100 qubits roughly, and I can do about 100 operations on this quantum computer, and then usually one of my qubits throws up an error and renders the computation useless. So let's look at how this whole quantum computing concept plays out for a very specific example on this table of where quantum computing, or where better quantum chemical calculations could have an impact, which is the electronic band structure and how it affects synthetic fuels. Electronic band structure is nothing else as how do electrons behave in a solid. And synthetic fuels, the example I want to look at is methane steam reforming, which is the process of using natural gas, taking natural gas, having it react with water and producing hydrogen. And this happens, or hydrogen carbon oxide, syngas, and that's then used to then make synthetic fuels. And this happens on a catalyst, so it happens on a solid material, often nickel oxide or palladium oxide, and that without that catalyst, this reaction won't happen. But still, for this reaction to happen, you need 700 degrees to 1,000 degrees Celsius, very high pressures. It's a very, very carbon-intensive, energy-intensive type of reaction. So if I could design my catalyst in a better way, if I could really understand when, for example, my catalyst becomes inactive, when it breaks, how I could change the material to lower the necessary temperature, I could save vast amounts of energy. I could improve this reaction, and I could have a huge impact on global carbon emissions. So what would it take to then calculate the properties of this catalyst, the electronic band structure, on a quantum computer? This is work we've recently published. It would take about 10 billion operations on 5 million qubits and approximately 8 days of runtime. So the calculation would take approximately 8 days. And now I think you're losing faith with me, because I just told you that today's quantum computers can do like 100 operations on 100 qubits, and this is obviously a huge technology gap. And yes, it is. And at the heart of this technology gap is the problem of how I correct the errors that these qubits throw up well enough so I can do enough operations so the calculation isn't completely useless. So this is the biggest technology challenge, how to make a quantum computer that is error-corrected. Quantum error correction is fundamentally the way in which we use lots of qubits, lots of unstable qubits, and make one long-time stable or logical qubit out of it. I use lots of qubits because then I can encode redundancies in these qubits. So if one of them breaks, I still have the other ones. But it is also very complicated because, again, these are all quantum mechanical particles. So if I measure them, they fall flat. So I have to have a very, very smart way of encoding my information, measuring this information, then guessing where the error happened, and then correcting the error. And just to illustrate a tiny bit of what kind of classical information processing challenge this is, on top of all of this quantum mechanical stuff, for quantum error correction to happen, we need to process hundreds of terabytes per second of data in real time, and this is about the same as Netflix's worldwide data rate. Okay, so now I've told you a lot about the challenges. Is there any hope that quantum computing might close this technology gap in time for us to make use of it to accelerate innovation in material science and chemistry to help climate change? Well, if you look at quantum hardware roadmaps, so the roadmaps of people who build the qubits, actually, yes, in 10 years' time, we could have quantum computers that are the right order of magnitude in size, that are error corrected, so we can actually compute that catalyst for methane steam reforming on them. This is obviously a relatively optimistic roadmap. It's based on Google's roadmap, which are building superconducting qubit quantum computers. But they've hit their first milestones, so we're pretty optimistic that they will hit their next milestones as well with the right level of effort, with the right level of investment which they have. And they won't do it alone. Companies like Riverlane, where I work, are working very hard on this classical information processing problem that is connected to quantum error correction to enable some of the very crucial steps in this roadmap. And there's something else that makes me quite optimistic. Because I told you 10 billion operations, 5 million qubits, approximately 8 days of runtime, but this is based on the current best available methods and algorithms that we have for computing that chemical on the quantum computer. And improvements in the algorithms, which I haven't really talked about today, have in the past meant that, that the size of the quantum computers that we need to do actually useful computations have become smaller. For example, there has been a new way of mapping that chemical problem onto the quantum computer called qubitization, which brought the runtime that I need, the time that I need for the calculation to happen, down from hundreds of thousands of days, in case of this iron-carbene complex, that's an important chemical for solar cells, down to just a couple of days. So down to a time that I would be willing, as a quantum chemist, as a computational chemist, to wait. All of this makes me quite optimistic that quantum computers will be ready in time to accelerate the innovations that we need to make better batteries, to improve industrial processes for making chemicals, and to design better drugs to help with sustainability and with climate change. Thank you, and I'm open to questions.